All right, how's it going, guys? Got another few recitation example problems to go over with you. Should be pretty useful for the exam that's coming up for you guys on Wednesday. If you're watching this, this will be up Monday night, so a couple days of studying. Let me know if you guys need anything. Should be all right. It's not that tough an exam. It's really not terrible. But yeah, study up. If you have any questions or concerns, drop them in the comments below or shoot me an email. You guys know the deal. Anyway, so let's get in this first one up here. This is going to be dealing with forces on like a slanted plane object, right? There's a little bit of an angle right here. So we've got the gate is 5 feet wide, hinged at B, and rested against a smooth wall A. We want to find the force on the gate due to seawater, horizontal force P pushing right here at A, and then the reaction is at point B. So first off, let's go ahead and draw our free body diagram. Just get that out of the way, so I'll do it over here, I guess. Okay, so let's get our axis going. So we've got, gonna have gate like that, and this is point A up here, so we're gonna have this P pushing right there. I'll call this BY and BX. And I don't care too much about the orientations of my forces. It's fine. Take the magnitude of them. This isn't statics class. We know what's going on. And this theta right there, right? And then we're going to have the force of the water pushing down here, right? And I very intentionally drew it like comically low on the object, right? So because the centroid is right here. So this is going to be way lower, right? Just so you can illustrate it better. But let's get some stuff going about the gate, right? We know this is 10 feet. 10 feet long, right? 8, 6, 10. It's a Pythagorean triple, as they say. And this is our centroid right here. And so with that, the height of the centroid, that's going to be 3 feet from the bottom. So it'll be 12 feet from the top. And now we're pretty much ready to go. For the force on from the seawater, that's easy enough. We know force of the water for any object, doesn't matter if it's slanted or not or whatever. That's just rho g, height of the centroid, times the area of the object you're talking about. In this case, we're given the 64 pounds per cubic foot. That is rho times g, all right? That's a specific weight. So we can just pull that in right away. So this is 64. Then the height of the centroid is 15 minus 3 from the top, so it's 12 feet. Then the area, it's 5 feet into the page. This is 5 feet wide. And then 10 feet long, right? 8, 6, 10. So this equals this FW. All right, this FW should be at 38,400 feet. Oh, 38,400 pounds. Ugh. All right, that's nice and easy. That's cool. But in order to find these reaction forces, right, we drew a little free body diagram. We're going to have to do some sort of moment equation. So we're going to need to know where this force is acting. And so that's where we invoke our COP formula, center of pressure formula. So Y COP. And when I do this, this Y COP for me, I always do this in terms of it already being slanted with the gate, right? It's along the length of the gate. So this little tiny number we're going to end up getting will be the difference between the centroid right here, and then this other little dot is the COP right there. And so the Y COP will be this little diagonal bit between the two, okay? That's what my formula gets me. There's other ways to go about doing it, but that's how I get mine. So this is just the classic IXX sine theta over height of the centroid vertical to the water, right, times area. And theta equals tan inverse of 6 over 8. And this equals like 36.87 degrees. Now I'm just going to write theta. I don't want to have to write that whole number every time. So anyway, let's do the YSOP. This is IXX, moment of inertia of a rectangle. It's 1/12. Base is going to be 5. And the height is the total height of the object, right? So 10 cubed. base times height cubed. 1/12 base height cubed is ISS for a rectangle, if you didn't know. Then sine theta, right? Sine theta, and then I'll just do 1 over 12 times 50, right? So this will get you YCOP equals 0.4167. This is along the gate. Along the gate. And of course, that's below the centroid, right? Obviously, just logically think about that for a second. So we've got the force, right? We got the force of water, and we know where it's acting. So now we can go and start solving all this stuff. So to solve for P, let's do P first. So let's take a moment up about point B right here. And I know this isn't like a fully complete free body diagram. We don't care that much. It's fine. Just give us the general picture of what's going on. We're not going to grade you super hard on your free body diagram. So let's take a moment up about point B. We'll call that positive. So that equal to 0. This is equal to, so coming this way, we've got negative FW times, I'm going to do 10 minus 5.4167, right? 4167. And I did 10 minus that because I'm taking points from B, right? And this 0.4167 is like this distance here. It's just easier math for me. You get the idea. And then just P times 6. Alternatively, you know, sometimes I like to have all of my forces like in the same plane, right? Like tilted with the same angle, right? Like that. So you could also do like 10 times P sine theta or whatever if you really wanted to. Mathematically, it's all the same thing. So we're solving for P. We know FW, we know all that. Let's go plug in. End up getting P is equal to 29,333 pounds. So that's easy enough, not too bad. And now for the other ones, we can just do basic force balance. So let's do some forces in Y equals 0 equals, this will be negative FW cosine theta plus BY. Okay. So again, we know FW, we know cosine theta is solving for BY. BY should equal 30,720. 30,720 pounds. Ish, and I rounded a few of these on my my cheat sheet that I'm looking off of right now. I rounded a couple of these. It's totally fine. Get us in the ballpark, especially like for an exam. As long as you're not off by like a order of magnitude, you're gonna be totally fine. Same thing for x direction, except this will be positive FW sine theta, right? I'll say minus BX and minus P. Again, we already solved for P. We already know that. Solve for BX. BX is equal to negative 6293. Now, of course, that negative sign just means I drew my arrow in the wrong direction. It's totally fine. We care about the magnitude of it, right? It's okay. Anyway, pretty basic one. I mean, like, this is really about as hard as we can make these ones. Once we realize the trick to them really doesn't take very long at all. I mean, I could freehand this like 3 minutes. Like, it's really not too bad. Just remember your base equations and you'll be good to go. Now, moving on to number 2, this is a curved surface one. And the answer key that goes along with the recitation that I will post is pretty verbose and pretty yappy when it comes to this. There's a little shortcut trick that I like to do with these that works really well for situations like this, but I don't think works every time, or at least it's clunky if you try and use it every time. So for like a basic one, just use the standard way of doing it, but for these ones, this works pretty well. Anyway, we've got a cylindrical dam that separates two different fluids, right? Row 1 and row 2. And we want to obtain expressions for the net horizontal and vertical forces on the dam that has diameter d and width w. And we're neglecting the weight of the dam itself, right? I stole this from an old homework from a couple semesters ago that we put out. And I think for like a part B, there was, we had to find the weight of the dam that counteracted all of this stuff, but we don't care about that right now. That's just complicating things for no reason. This gets the point across just as well. So what I'm going to do here is I'm going to break this into halves, all right? So I'm just going to break this problem in half. So I'm going to do everything with this half first. Well, I'm going to do like left side, then right side. Let's find the horizontal forces first because it's really easy to do that. So let's go left side. So I'll say FLH, force left side horizontal. This is just the horizontal projected area that we're looking at here, like this. So if we look at this from the side, right, we're gonna have some force coming there. And so this is just the same rules as like a rectangle. All right, so it's just gonna be rho g height of the centroid times the area. But this is just the horizontal projected area. So plug that in. So we got rho 1 g, height of the centroid is d over 2. Right, because we're looking at a quote-unquote rectangle over here, so the centroid is d over 2. Then the area is just d times w. So let's clean that up a little bit. Equals 1/2 rho 1 g d squared w. Cool. Now let's do the same thing for the right side. We'll go r. So FRH. Again, is equal to now rho 2 g height of the centroid times the area, where this is rho 2 g height of the centroid now is d over 4, right? Half of d over 2 is d over 4. Times the area is d over 2 times w. So again, do some cleaning. Also be 1/8 rho 2 g d squared w. Cool. So now I'm going to just come over here and do the sum of forces over here. So sum of forces in x, right? And this other force would be like that. I know I'm writing really tiny, but it's okay. This shouldn't be the most mind-blowing thing in the world. Obviously, this force will be going that way, and then that force will be going that way. So like this doesn't necessarily equal 0. It'll equal F net, right? F net x. Of course, once we go and do all of this stuff, we can find the case in which it would equal 0. But strictly speaking, this just equals F net x. And, if we want to say x is positive in that direction, we'll have FLH minus FRH. And so F net x. I'm just going to clean everything up right away. I'm going to factor out the g d squared and w. So it'll be g d squared w 1/2 rho 1 minus 1/8 rho 2. All right, and that's easy enough, right? Cool. So you can see, if you wanted this to sum to 0, if you wanted the net force on this to be 0, you would take, set these two equal to each other. So you'd want rho 1 to be, what, 1/4 of rho 2. So that's cool. But obviously you can see if they were both water, you would have way more force on this side, right? So it doesn't have to be 0, but whatever. So there's that one. Okay, now for vertical, okay? So FLV, okay? And this is where things get a little tricky. This is where I do my shortcut, okay? If you go and look at like the answer key or something, it'll have all sorts of crazy math to go with it. And that's cool if you learn like that, that's totally sweet. But the shortcut for it, for a case like this, it works out mathematically that I always imagine, I imagine it like this, all right? So let's look at this left half of the dam like we did before, right? Where we have all of this being filled in by dam, okay? If you imagine completing, taking away this volume of dam and replacing it with just water, right? All that water wants to come rushing in, okay? This dam is like displacing the half cylinder full of water, okay? And so you can think of it kind of like a buoyant force sort of thing, right? All that water wants to come rushing in, and so that's the force that is associated with it. It's that volume of water that wants to come rushing in. So I can, mathematically works out to just be like this, where it's literally like a buoyant force thing. So if rho 1 g times the volume being displaced. All right, and what is that volume being displaced? It's literally just half of a cylinder. So FLV is equal to rho 1 g times 1/2 pi, and then r squared is d squared over 4 times the width of the dam. Cool. So there's that. Now let's do the same thing over here. Or FRV. Again, is equal to rho 2 g times the volume being displaced. So now the volume being displaced on this side, right? Imagine completing this, filling this back in with water. It's this volume being displaced. Now it's 1/4 of a dam. So FRV equals rho 2 g 1/4 pi d squared over 4 times w. Cool. And so now put them all together again. So we get sum of forces in y equals F net y. And again, we're disregarding the weight of the dam, so there's no other force. And so this equals FLV plus FRV. Right? And so again, just factoring out really quick. F net y is equal to, okay, I'm gonna take out the g d squared w pi. Now we're gonna do times 1/8 rho 1 plus 1/16 rho 2. Yep, and we are good to go there. Cool. And so yeah, that is the net force in the y direction. So, now, like, if we wanted to make like a part B for this, right, we can say, okay, what densities will the waters have to be for the x direction be 0, and what would the weight of the dam have to be, or what would the density of the dam have to be to get the weight to cancel everything out, right? Something like that. But yeah, the vertical component stuff can be kind of weird. Go back and look at that stuff if you really need to. As far as the lines of action go, for the horizontal forces, right, it would just be 1/3 from the bottom, because it's just a horizontal thing. So 1/3 from the bottom in both cases, with respect to the height of the water, right? And then for the y direction, it would just be the centroid of the respective volume, right? So like, be like kind of right there or whatever, and then kind of like right there-ish, right? Pointing straight up. This is a buoyant force thing, so it'd be pointing up. And then yeah, the resultant would kind of be the combination of those two things. So not too tricky, but definitely a topic to review if you're shaky with it. All right, then lastly, the very last problem, pretty easy, pretty basic one. We have a ball of plastic with rho p equal to 48 kilograms per cubic meter. And it's half submerged in water. We want to find the tension force and the tether holding it down. Will this force change if it becomes fully submerged? And take the diameter to be 0.6 meters. All right, so first off, let's draw a free body diagram. We've got the weight of the ball like that, and then we've got some buoyant force pushing up, and then some tension force pulling it down. So some forces in y equals 0 equals FB minus T minus W. So we can say the tension force that we're trying to find is equal to FB minus W, where W, of course, is equal to rho plastic times gravity times just the total volume of the ball. I'll say V ball. All right. Cool. And so this is 48 times 9.81 times 4/3 pi. 4/3 pi r cubed is the volume for ball. So r cubed is diameter cubed over 8. So I'll say 0.6 cubed over 8. and this should be equal to 53.2 newtons. Okay, and the buoyant force, FB, is equal to density of water, right? Whatever liquid we're floating in, that's the density we're talking about, times gravity times the volume being displaced. Okay, now in this case, the volume being displaced is just half of this sphere, right? It's only half submerged. So this will be 1,000 times 9.81 times 1/2, 4/3 pi 0.6 cubed over 8. All right, and this will be equal to 554.7 newtons. So we've got T equals FB minus W. So plug that in. T should be equal to 501.5 newtons. Cool, just super simple little force in a cable sort of thing, right? Holding it down. And so brings us part B. Will this force change if it becomes fully submerged? Well, of course it will. Tension will have to increase, right? Because when you finally fully submerge the whole thing, right, this volume displaced, V disp, becomes, it's not 1/2 anymore, it's all the way done, right? It's all the way underneath. So this 1/2 will go away and it'll be the full thing. It'll be a 1 instead of 1/2. So the buoyant force will double, right? If the buoyant force doubles and the weight stays the same, you need to increase the tension force to keep it held underneath the water. Pretty basic little thing. And then, I liked asking the question in my sections, what would happen if you moved the thing, instead of just barely underneath the water, moved it down 10 meters underneath the water, right? So it's super far down. Well, that once you fully submerge the thing, the tension force, the buoyant force cannot increase anymore once it's fully submerged. As soon as you hit that maximum volume threshold, you've got all the buoyant force you can get out of it, right? Nowhere in these equations is the actual height of the ball underneath the surface of the water relevant, right? So once you get it fully submerged, boom, that's the most buoyant force you can get, all right? Just a little conceptual thing that some people struggle with sometimes, but all pretty basic stuff. I think you guys should be all right for the exam. I wouldn't worry too much about it. But yeah, if you need anything, just let me know, and should be good to go. All right, thanks, guys.